All right, let's talk about something absolutely critical in our digital world: system availability. We're going to dive into how services go from being super fragile and prone to failure to being rock solid and always on. Let's jump in.
So I want you to think about this for a second. When was the last time Netflix was just down? Or your banking app? It almost never happens, right? And that's not luck. It's some seriously clever engineering working behind the scenes to keep things running 24/7. So what's their secret? Well, it all boils down to this one key concept: availability. Really, it's just the percentage of time that a system is up and doing what it's supposed to do. The formula looks simple, right? Uptime divided by total time. But trust me, getting that percentage super high, that's the hard part. You can think of it as the ultimate report card for any online service. Okay, this is where it gets really interesting. In the industry, we talk about availability in terms of the nines. And look at the difference here. It's just wild. 99% availability, that sounds pretty good, doesn't it? But that means your app is down for more than 3.5 days a year. Now, jump all the way to 5 nines, that's 99.999%, and your downtime for the entire year is just over 5 minutes. That huge leap is what separates a decent service from a truly critical, can't ever fail one. So, the big question is, how do we climb that ladder and get more nines? Well, our first line of defense, and honestly, the most important one, is something called redundancy. Imagine this. You've built your awesome new app, and it's running on a single lonely server. What happens if that server's hard drive dies? Or, someone accidentally unplugs it? Poof, game over. Your whole service just vanished. That right there is what we call a single point of failure. And how do you fight a single point of failure? You guessed it, redundancy. It's a beautifully simple but powerful idea. It just means having a backup. Having a spare tire in your car. If one component fails, no big deal, the backup just takes over and you stay online.
Now, when we talk about redundancy, it usually comes in two main flavors. First, you've got active-active. This is where all your servers are running at the same time, all sharing the workload. If one goes down, the others just pick up the slack. Easy peasy, super efficient. Then there's active-passive. Here you have one main server doing all the work and the backup just sitting there, waiting. If the main one fails, the backup jumps in and takes over. This is a bit simpler to manage, especially for things like databases, but there's a tiny bit of a delay during that switchover.
Okay, so making copies of our servers is one thing, but what about the data? The really important stuff. That brings us to the next, much harder challenge: protecting the database. And this is where things get really tricky. See, your web servers are usually stateless. They're like workers with short-term memory. You can replace one, and it doesn't matter. But your database? That's the stateful heart of your entire system. It holds all the memories, all the critical information. If that goes down, you're not just offline. You could actually be losing customer data. And that's a nightmare. When it comes to protecting that data, there are two terms you absolutely have to know. The first is RTO, Recovery Time Objective. Just think of it as a question. What's the maximum amount of downtime we can tolerate? Is it okay to be down for an hour? Or does it need to be back up in 10 seconds? The answer to that question completely changes how you build things. And the second term, which is just as important, is RPO, Recovery Point Objective. This one isn't about downtime, it's about data loss. The question here is, how much data are we willing to lose? Are we okay with losing the last hour of transactions, or can we only afford to lose, say, the last 1 second? If you need a really low RPO, you have to be copying your data almost constantly. So let's put that all together. Here's how a slick, automated database failover actually works. Step 1, your main database dies. Bam. Instantly, an automated health check sees it's gone. Step 2, it promotes one of those standby copies, the replica, to be the new primary. And finally, step 3, all the traffic from your app gets rerouted to the new primary. The amazing part? This whole dance can happen in just a few seconds. All right, so we're feeling pretty good. We've got backup servers, we've got a backup database. But what if the whole building goes dark? A massive power outage, a fire, a flood. We need to zoom out and think even bigger. And that's where geographic redundancy comes into play. You can start small with multiple servers in the same data center. That protects you if one machine fails. But the next level up is using multiple availability zones, or AZs. Think of these as separate, distinct data centers, but in the same general city. If one building loses power, your app keeps running in the other. And for the ultimate survive anything setup, you go multi-region. You literally run your application in different parts of the world. That way, even a massive earthquake on one continent won't take you down.
And here is the secret sauce. This is the math that proves why redundancy is so unbelievably powerful. If you have services that depend on each other in a chain, in series, your overall availability actually goes down. It's your weakest link. But if you run them in parallel, like two backup servers, the odds of both of them failing at the exact same time becomes incredibly small. Look at this. Two servers that are each 99% reliable, when run in parallel, give you 99.99% availability. That's not just addition, it's multiplication. It's magic.
Okay, so we have backups for our backups. We're feeling pretty indestructible. But what about the sneakier kinds of failures? The ones that don't just cause a big crash, but instead slowly, quietly poison the system and bring everything grinding to a halt.
Because a truly resilient system isn't just about surviving those big explosions. It's about containing the small fires before they burn the whole forest down. This is the danger of a cascading failure. All it takes is one tiny service to start acting slow, and that can trigger a chain reaction that takes everything down.
Our first defensive tool against this is the circuit breaker pattern, and it works exactly like the circuit breaker in your house. If you plug in a faulty toaster and it trips the breaker, the power to that outlet is cut, but the rest of your house is fine, right? Same idea here. If our application is talking to a service that's failing, the circuit breaker trips. It just stops sending requests to the broken service for a bit. This is huge. It gives the other service time to recover, and it stops our app from wasting all its time waiting for an answer that's never going to come.
Next up, we have the bulkhead pattern. And the analogy here is just perfect. Think about a big ship. It's divided into separate watertight compartments. Why? So that if you get a hole in one part of the hull, only that one compartment floods. The bulkheads contain the damage, and the ship doesn't sink. We do the exact same thing in software. We create isolated resource pools for every external service we talk to. That way, if one of those services goes crazy and starts consuming resources, it can only flood its own little compartment. It can't sink the whole ship.
And finally, we have what might be the simplest, but maybe the most important pattern of all: timeouts. It's a dead simple rule. Every single time your application makes a call to something else, a database, another API, anything, it has to have a timeout. You have to tell it, hey, if you don't hear back in 2 seconds, just give up and move on. Because without that, a single slow service can make your requests hang forever. And soon, all your resources are tied up and your whole system just melts down. So we've done it. We've built this amazing system. It's got redundancy, it has automated failover, it's got circuit breakers and bulkheads. It should be basically bulletproof, right? Right? Well, how do we actually know?
And that brings us to the ultimate test: chaos engineering. Now, this sounds a little crazy, but it's brilliant. It's the practice of intentionally breaking things in your live production system. You literally go in and randomly shut down servers, or you make the network slow and unreliable on purpose. Why? To see what happens. It's the only way to prove that all those automated defenses you built, the failovers, the circuit breakers, actually kick in and work when you need them most.
Which really brings us to